Welcome students. We are back with another lesson. In this lesson, we will discuss the working of the astronomical telescope when the final image is formed at infinity. Okay, after discussing the working, then we will derive the magnifying power of the astronomical telescope when the final image is formed at infinity. Okay, now, usually your astronomical telescope is in this configuration where the final image is formed at infinity. Now, why is it so? This is because suppose you have your human eye, okay, and suppose you have one object. This is your object A, which is placed in front of your human eye, and there is another object B, which is placed at infinity from your normal human eye. In such case, okay, if it is placed at infinity, let us consider this is not here, okay. Okay, so consider a object which is placed in front of your eye and another object, your object B, which is placed at infinity. Now, if you look at your object A as compared to your object B, okay, the object B which is placed at infinity, that means very far from your normal human eye, okay, very far. Yeah, you can see the distance, but in actual case it will be very large. Okay, this distance is very large. Now my point is that suppose if you look at this two objects, your object A and your object B, in which case will it be more stressful on your human eye? It will be when you are observing your object A. Okay, so usually what happens is that your astronomical telescope is usually adjusted so that the final image is formed at infinity. Fine. So that it becomes less stressful to our eye. So such arrangement is also known as your normal arrangement. Fine. Now coming to your astronomical telescope, the astronomical telescope consists of two converging lenses. By converging lens, I mean convex lens. The first lens is your objective. This objective has a focal length FO, and the objective has a large focal length and it has much greater aperture, means it has more thickness. By aperture, I mean thickness. The second lens is your eyepiece. The eyepiece has a focal length Fe, which is short or which is small focal length as compared to your objective. So the focal length of objective is greater than the focal length of the eyepiece. Apart from having a small focal length, it also has small aperture, means the thickness of this eyepiece is also small. Fine. So let's come to our astronomical telescope. Now, in such case, okay, consider this is your astronomical telescope. Okay, now let us say a object AB is placed at infinity. Okay, this object AB produces rays. This rays falls on your objective. Okay, the rays falls on the objective and it forms the image at this point. Can you see? This is the image A dash B dash formed by the object AB, which is placed at infinity. Now, if you look here, the image form is small as compared to your object, so it is diminished. Fine. Apart from being diminished, that is small in size, it is inverted. Okay, the image form is inverted, and also can you see the rays are actually intersecting, so this is a real image. So your objective forms the image of the object AB A dash B dash. Okay, this image is real, it is inverted, and it is diminished. Now, since your object is placed at infinity, therefore the image is formed at the focal length of this objective. Fine. So this distance represents the object distance. Okay. And since this is the focus of the objective, therefore this distance also represents the focal length of the objective, which is denoted here. Fine. Now, now we will introduce our second lens. This is your eyepiece. Now, our eyepiece will be placed in such a position so that the image formed by the object using your objective, this image A dash B dash will act as a virtual object for your eyepiece. Fine. But the condition is that this object should be placed at the focal length of the eyepiece. Now, why is it so? Because if the object is placed at the focal length, the final image will be formed at infinity. Fine. So, let us place our eyepiece. Okay, now the object A dash B dash is placed at the focus of the eyepiece. Okay, now this object A dash B dash forms the image at infinity. Fine. So let us summarize. Okay, your object AB, which was formed at infinity, which was placed at infinity, forms the image A dash B dash at the focal length of the objective using your objective. Now this image A dash B dash will act as a object for your eyepiece. Now this object is also placed at the focal length of the eyepiece. Fine. So yeah, if this distance, okay, since this is your object for the eyepiece, in that case this distance will represent the object distance, and since it is placed at the focus of the eyepiece, then this distance will also represent the focal length of the eyepiece. Fine. Now this eyepiece will form the final image at infinity. So I can say the object forms the final image at infinity, and the rays coming from this infinity falls to our normal human eye. So this arrangement of the astronomical telescope is also known as your normal arrangement, or I can also say normal adjustment of the astronomical telescope. Fine. So this is the working of the astronomical telescope when the final image is formed at infinity. Now next we'll derive the magnifying power in normal adjustment. So your magnifying power is defined as the ratio of the angle formed by the object AB. So if you look here, your object AB is making, or it is subtending, an angle alpha. Fine. Now this is your angle alpha should be equal to this angle. Why? Because these two angles are your vertically opposite angles. Fine. So the magnifying power, okay, this is the angle subtended by your object AB. Coming to our image, the okay, for image, consider your eye to be placed at the eyepiece. Okay, consider your eye at this eyepiece. So the angle subtended at the eye by the final image, what is that angle? This green angle. This is the angle subtended by the final image. This angle is beta. So the magnifying power is defined as the ratio of the angle subtended by the final image to the angle subtended by the object when both the image and the object are placed at infinity. Fine. So this is what I have written here. Okay. So your magnifying power, which can also be written as m, equals to beta upon alpha. Now, since your alpha and beta are small angles, in such case I can write beta as tan beta, alpha as tan alpha. Okay, now let's go back to our figure and see what is tan beta and tan alpha. For tan beta, consider this green triangle. Okay, let me just zoom on this triangle. So tan beta, okay, consider this green triangle. Okay, so tan beta is the ratio of the opposite side a dash b dash upon your adjacent side, this eb dash. Okay, so tan beta equals to a dash b dash upon eb dash. Fine. Okay, now for your tan alpha, you can consider this yellow triangle a dash o b dash. Fine, let me just zoom here. So for tan alpha, you can say it is tan alpha is the ratio of the opposite side a dash b dash upon your adjacent side o b dash. Fine. A dash b dash upon o b dash. Fine. So I can write my tan beta as a dash b dash upon eb dash and tan alpha as a dash b dash upon ob dash. Okay, now if I simplify this one, okay, this ab dash and this a dash b dash can get cancelled. This eb dash will come to the denominator and this ob dash will go to the numerator. This is what I have written here, ob dash upon eb dash. Now, what is OB dash and EB dash? Let's go back to our figure. This is your distance OB dash. Now, this distance, okay. Now, since A dash B dash represents the image for your objective, so this is the image distance. Okay, this image is formed at the focal length of the objective. So this distance also represents the focal length of the objective. Therefore, I can say OB dash is the distance of A dash B dash from the objective. Fine. And one more important point. Okay, look, is this direction measured in the direction of incident light or opposite to the direction of incident light? It is measured along the direction of the incident light. So according to sign convention, this distance, which can also be written as FO, should be positive or negative. It should be positive. So I've written here OB dash equals to plus FO. This represents the distance of A dash B dash from the objective. And since it is along the direction of the incident light, I've put a positive sign here. Coming back, now look at your distance EB dash. This distance denotes the distance of the object A dash B dash from your eyepiece, and this object is placed at the focus of the eyepiece, which can also be represented by focal length of the eyepiece, which is FE. Now, look at this distance. Is this distance measured in the direction of incident light or opposite light? It is measured in the direction of opposite, or I can say against the incident light. Okay, your incident light is in this direction, whereas you are measuring this distance from the center to the object EB dash, which is opposite to the incident line. So in such case, this will be positive or negative, this distance? It will be negative. So I've written EB dash equals to minus of FE. And what is this FE? This is the distance of the object A dash B dash from the eyepiece. And since it is against the incident light, so I've put a negative sign here according to the sign convention. Fine. So let us substitute these values here. So your magnifying power can be written as M equals to minus FO upon FE. So this is the magnifying power of the astronomical telescope in normal adjustment. Fine. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I can re-explain it to you again. So again, thank you.